Alright guys, so today we're going to go over the 2018 UIL number sense test, so let's get started. Oh, I already had some writing here. Let me erase that. So, one thing I could do here for number 1, I can do the 118 minus the 181 right off the bat. And so that's going to get us a negative 63. So I'm going to take that negative 63 and I'm going to add it to the 811. So 811 minus 63, that's going to be 748. For number 2, we're doing 40 times 125. So whenever you're multiplying something by 125, so like let's say I have some number A times 125, really that's the same as dividing it by 8 and then multiplying by 1,000. So you can think of it as multiplying by 8, or dividing by 8, and then adding 3 zeros. So an example would be like if I had 24 times 125, what I could do is I can divide the 24 by 8, that's 3, and just add 3 zeros, so 3,000 would be our answer. Now let's apply this trick to question 2. So we're going to take the 40 divided by 8, that's 5, and then we're going to add those 3 zeros. You can think of it as we're shifting the decimal point 3 spaces to the right. So 5,000 is our answer. For number 3, what we can do is we can make the 5/8 into 10/16. Now why would we want to do that? When we want to get, when we're adding fractions, it's best to get these fractions to have like denominators. So you can just add the tops. So if I say 5/8 is 10/16, which it is the same, I'm just doubling the top, doubling the bottom, still the same number, then I can say I have 10/16 plus 3/16, which is just 10 plus 3 over 16. That's 13 over 16, which is our answer. Beware, by the way, guys, if they're asking for decimal or proper fractions, sometimes they'll trick you like that. So you gotta make sure you're writing what they ask for. Okay, so for number 4, this is a pretty common trick. So if I have increasing numbers like 1, 2, 3, like this, just like the whole numbers, times 9, and then I add the next number, which would be 4, it's always just this many ones. Always. So if I had 1, 2, 3, 4, 5 times 9 plus 6, well then the answer is just 6 ones. And so for this question, because this number right here is 4, our answer is 4 ones. So for number 5, that's 289. You want to have your squares up to 30 memorized. So memorize. So you could use flashcards, you could use Quizlets. I like just using flashcards to memorize these. You practice for like an hour and you got them all memorized. So yeah, just memorize those squares up to 30. Start with 1 to 10. probably know that from just times tables. Then 10 to 20, memorize like 13 squared, 17 squared, 19 squared. And you increase it to the 20s, so like 23 squared, 27 squared, 29 squared. And before you know it, you have all your squares up to 30 memorized. Alright, so number 6, 3 over 40. So whenever you have a number, it's like a over 40, the decimal representation, it's always equal to like 25, or I should say actually the percent representation, because that's what we want here. It's always equal to 2.5 times whatever a is. So let's say if a was 10, for example. 10 over 40. Well, then its percent representation is going to be 2.5 times 10, so 15 or 25%. And so in this case we have a 3 right here. So 3 times 25, it's like 3/4, that's 75 cents. So 3 times 2.5, that's going to be 7.5%. Alright, so number 7 is a pretty good one. So here you could see that we have 16 times some number added to 16 times some other number. So let's say I have a common factor a, like a times b plus a times c, right? Some common factor a. Well, if I factor that a out, I can simplify this expression to be equal to a times b plus c. So let me rewrite this, substituting in 16 for our a, 28 for our b, and 22 for our c. So really, doing 16 times 28 plus 16 times 22 is the same as doing 16 times 28 plus 22. And that's convenient because 28 plus 22 is 50. And when I'm multiplying by 50, it's like I'm dividing by 2 and then multiplying by 100. So it's like I'm dividing by 2. If I divide the 16 by 2, I get 8. And then I add 2 zeros. Shift the decimal place to the right 2 times. And so my answer here is 800. Okay, so for number 8, we have 11 divided by 2.5. So when you're dividing by 2.5, it's like you're multiplying by 0.4. And the reason is because when you are dividing by 2.5, that's the same, so this is the same as multiplying by 1 over 2.5, which is the same as multiplying by 2 over 5, which is the same as multiplying by 0.4. So really, when I'm doing 11 divided by 2.5, I'm doing 11 times 0.4. That's just going to be 4.4. So whenever you see this dividing by 2.5 term, just think multiply by 0.4. Okay, number 9. Largest prime divisor of 76. So this is a real important thing to know how to do. Getting the prime factorization. In the prime factorization of a certain number. Because getting the prime factorization, that's a trick or like a step we use in a lot of problems. One being like, what's the largest prime divisor? Like this question's asking. Another might be like, how many divisors does this number have? We got to do the prime factorization as well. So how do we do the prime factorization? We have 76 here. So you want to start with two numbers that you know, multiply to 76. So I know that, for example, 4 is a factor of 76. Meaning that 76 divided by 4, so 19, is another factor of 76. And 19 is prime, so let me just circle it to show it's prime. My factor tree on that right side ends there, once I've reached a prime number. On the left side I have 4, which is not a prime number, meaning I can break it down further. So the 4, it can be broken up into 2 and 2. And those are prime numbers. So now the tree is stopped. Now I count up how many prime factors I've got at the end of this process. So I have 2 2's, so that's 2 squared, and 1 19, so like 19 to the first. This is the prime factorization of 76. So it shows that 2 squared times 19 gives us 76. These are the prime factors, 2 and 19. So let's say if the question asked, how many prime divisors does 76 have? I would only say 2, those being 2 and 19. Now we want to know what's the largest prime divisor. 19 is greater than 2, so 19 is our answer. In this question, like if you know that 76 breaks up into 19 and 4, and you know 19's prime, you don't really have to break up the 4 anymore because it wants the largest prime divisor. You've already got it. So you wouldn't have to fully break it down, keep in mind the exponents. At that point, you'd already know 19's the largest prime divisor. Right? Number 10. So we have 158 times 262. So I think, well, I guess I should mention this in case you're new to number sense. Any question that's a multiple of 10, so 20, 30, 40, 50, or any question that has this asterisk, right? Those are what we call estimation questions, meaning you only have to be within 5% of the true answer. So we can mess with the numbers a bit. We can round, which is what I'm going to do here. Because multiplying this out is kind of messy. So instead, I'm going to round this to 160. And I'm going to multiply this, round it to 260. Really, what I'm doing here is, like what I can do now, is I can just multiply 26 times 16 and then add 2 zeros, right? Because I pulled out these two factors of 10. And that's a lot easier than multiplying 158 and 262. But usually there's no set way to do these estimations. You have to get creative sometimes. But rounding is a big tool for us in estimation questions. So 26 times 16. So how can I multiply these two numbers? Well, here is one of the most important number sense tricks to learn. It's what we call foiling. Now you may have learned about FOIL in Algebra 1. First, outer, inner, last. So usually in Algebra 1 we used FOIL to describe the process of multiplying these binomials, like this. You would start with the first, then the outer, then the inner, and then the last. And it's kind of the same way for multiplication. So let me demonstrate. Let's work with big numbers, 53, 71. So how can I multiply this fast? Well, what I'm going to do is I'm going to multiply the first digits. In this case, what I'm calling the first digits is the ones digit. So like I'm reading left to right. So I'm going to multiply the first digits. So the 3 and the 1. And that's going to come out to 3. So I'll write my 3 down. Next, I'm going to add the products of the inner and outer numbers. So let's get the products. So 3 times 7, 21. 5 times 1, 5. Now I add those products together, 21 plus 5, that's 26. So I'll write the 6 down. I'll carry the 2. One of the ways you could remember how much you're carrying, you just hold out 2 fingers in your non-writing hand while the other hand you're writing. So this, I guess saves me some time. So I'm carrying 2. Then my last step is to multiply these last numbers here. So 5 times 7, that's 35, plus the 2 I carried, that's 37. Because it's the last step, I don't have to just write the 7 and carry the 3. I can now just write what I've got, 37. And so that's how we FOIL. This is how we can multiply any 2-digit number. Let's try it again. Let's come up with a good number. How about 37 times 87. So let's remember our steps. We're going to multiply our first digits, our ones digits. So that's 7 and 7. 7 times 7 is 49. I'm going to write the 9, carry 4. Next, I'm going to add the products of my inner and outer numbers. So my inner numbers are 7 and 8. I get their product, that's 56. My outer numbers are 3 and 7. I get that product, that's 21. So 56 plus 21, that's 77. Plus the 4 I carried, that's 81. So I'm going to write down the 1, carry 8. Now I don't have 8 fingers, so I've just got to memorize I'm carrying 8. So 3 times 8, that's like our last step. That's going to be 24. Plus the 8 I carried, that's 32. And now we've got our answer. So again, this is how you can multiply any 2-digit number. And it's extremely valuable to know this trick in number sense. You'll be using it all the time. So now, I think we're ready to solve this estimation question. If you remember what we started with, is 158 times 262. I rounded these numbers to 160 and 260. So getting the product of these two numbers is like getting the product of 26 and 16 and then multiplying by 100. Because I pulled out two zeros. You can think of it as I pulled out two zeros, and so I got to put them back at the end. So 16 times 26. So let's remember our steps. 6 times 6 is 36. So I'm going to write down the 6, carry 3. Then I'm going to get the sum of the product of our inner and outer terms. So 6 times 2 would be the product of our inner. It's going to be 12. 1 times 6 would be the product of our outer. That's 6. So 12 plus 6, the sum of our inner and outer terms, that's going to be 18. Plus the 3 I carried is 21. So I'm going to write down the 1, carry 2. And then lastly, I'm going to do 1 times 2. That's 2 plus the 2 I carried, it's going to be 4. So 416 is the product of 16 and 26. But I'm not done yet. If I can write down the 416 here, now I got to add back these two zeros and this factor of 100 that I took out earlier. And so I'll just do that by adding two zeros here at the end. And that's how we do number 10. And that's a pretty close answer. So I have the answer key here on my phone. And for estimations, the way they write the answer key is they'll give you the range. So like a range from A to B. And if your answer falls within that range, you get credit. And so the range here is 39,327 to 43,465. And our answer that we got is right there near the middle. So this one was pretty good. It's pretty accurate. Alright, so now we can move on to number 11. So I have 430 divided by 9. So I'm just going to do long division. So 9 can't go into 4, so I gotta check if it goes into 43. How many times does 9 go into 43? It goes in 4 times. So I've got to subtract 36, which is 9 times 4, from the 43. Leaves me with 7. Then I drop down the 0. And it's just like elementary. And then 9 goes into 70 7 times. So I subtract 7 times 9, 63. If I write the 7, and this difference is going to be 7. And now, this 7 is my remainder. So the way I can express it here is by doing 7 over 9, like that. And so, again, the way I do this, 43 divided by 9, 9 goes in to 43 4 times with a remainder of 7, and then I drop down to 0. So how many times does 4 go into 7, 0? How many times does it go into 70? It goes in 7 times with a remainder of 7. And now I'll just put that 7 over 9 here. just long division for that one. Number 12. 6 is blank percent less than 25. So for these kind of questions, so 6 is blank percent less than 25. The way to calculate like what percent less something is than other things, so if I replaced 6 with, let's say, 27 is what percent less than 100. The way I'd solve for that percentage is I would take the difference of this number and this number, so 100 minus 27, and put it all over 100, this number here. This would give me 73%. And so I'm going to use that same formula for number 12. Question 12 says 6 is blank percent less than 25. So I'm going to do 25 minus 6 over 25. That gives me 19 over 25. And that is just going to be the same thing as 76 over 100, so 76%. Okay, so number 13. We have 80% of 80 minus 80. So that's the same as doing 0.8, 80%, times 80 minus 80. 0.8 times 80 is just 64. Minus 80, that's going to be negative 16. Number 14. So the way I do number 14, when we have two mixed numbers that we're adding, is I like to separate the whole number and fraction parts. So I can already add the 1 and the 1 together, which is 2. And now I gotta add the fractions. So how can I do that? So I can't easily turn the 5 into a denominator 7, or vice versa. And when you can't do that, it's best to use the butterfly strategy. So how does the butterfly strategy work? Well, I'm just going to add the product of this cross right here and this cross right here. So that's going to get me 25 plus 14 over the product of this cross, the denominators. So that's 35. So this comes out to 39 over 35, which is improper, so we gotta take out that 1. This is just 1 and 4 over 35. So it's like I have 2 plus 1 plus 4 over 35. As a mixed number, that's just going to be 3 and 4 over 35. So let's try again with the butterfly strategy. Let me make up two fractions. So let's say I had 5 over 8 plus 4 sevenths. So I'm going to do this cross plus this cross. So 35 plus 32, that's 67, over the product of this cross, here at the bottom. That's 56, so as a mixed number, that would be 1 and 11 over 56. And the cross, that works when you're adding any two fractions. Alright, so number 15. So you gotta know your Roman numerals. So let me list them out here. So I is 1. V is 5. X is 10. One way you can remember I is it kind of looks like 1, and the V, think 5, right, has a V in it, so V for 5. X, think like when you get a strike in bowling, you knock out 10 pins, you get a strike, and then X is the symbol for strike. Then we got L, so L is 50. Then I have C, which is 100. And think C as in century, 100 years. Then we got D, which is 500. And lastly, we have M, which is 1,000. You could think M, millennium, 1,000 years. So those are some, memorizing tricks. And so how can I read this mess of letters? Well, there's only really one unique property you gotta know about these numbers. So if I wanted to represent 1, I'd just write I. If I wanted to represent 2, I'd write 2 I's. 3, I would do 3 I's. And so you might think that to represent 4, I'd draw 4 I's. But that's kind of, too much writing. And so what we instead do is we write IV, 1 behind 5. So this is actually 4. Then I have V for 5. And how would I write 6? I wouldn't write 6 ones, right? That's inconvenient. Instead, what I can say is VI. That's 1 in front of 5. So 6, like 1 plus 5. And this kind of system works for pretty much all of the numbers, like going up. Let's say I go to, like how would I write 400? I wouldn't write 4 C's, I'd write CD. 100 behind 500. So 400. And so, for this question, I have a 1,000 here, a 100 here, and this term, that's a 10 and a 50. And the 10 is behind the 50. So we could say 100 behind 50. This XL term is 40. And then I got VI, that's 1 in front of 5. So that's 6. I put this all together. 1, 1, 4, 6. And Arabic numeral, that just means, regular numbers. Like 1, 2, 3, 4, 5. Those are your Arabic numerals. So I encourage you guys to kind of look up more about like Roman numerals if you're new to it. Because they usually ask a question on this, like every other test. So it's important to know. They also use like these Roman numerals to like signify like, Super Bowl numbers, like Super Bowl 55. They write it as LV. Alright, number 16. If 1 gram equals 0.4 0.04 ounces, excuse me, then 120 grams is how many ounces? So this is like a proportion. So I have 1 gram for every 0.4 ounces. Then I want to know how many ounces would I have if I have 120 grams. So question mark ounces. So this ratio should always be constant. Right? And so if this top is being multiplied by 120 to get from 1 gram to 120 grams, for this ratio to be constant, I gotta multiply the bottom by 120 as well. So they increase by the same factor, right? And that should make sense. Like, for something you're more familiar with, let's say I have 20 donuts. I have 20 donuts is 1 dozen. Then how many dozen is 120 donuts? Well, if I have to multiply by a factor of 10 to get from 12 donuts to 120, I gotta do the same for the dozen. So I'd have 10 dozen donuts. And this ratio should stay the same. 12 to 1, 120 to 10, same as 12 to 1. And so, what I need to do in this question is take that 0.04 and multiply it by the 120. So 0.04 times 120. To make it easier for myself, I'll pretend this is 4 times 120 divided by 100. Because, 0.4, that's just 4 over 100. And this part's still not 4 over 100. So really I have 4.8 ounces in 120 grams. So yeah, make sure you know to work with proportions. Okay, number 17, greatest common divisor. So what the greatest common divisor is, it's the greatest number that divides a set of numbers. And what it means to divide a number means when you divide it, there's no remainder. So, technically I could say, for instance, 24 and 70, I could divide both these numbers by 5. I could divide them by any number. But what it means to be a GCD, greatest common divisor, means that you get whole number quotients. So 5 doesn't work. The greatest common divisor here, in this case, would probably be 2. Yeah. And so how do we find the greatest common divisor? We just kind of, think what factors work. Sometimes it's really obvious, sometimes it's not. In this case, I know all of these are multiples of 12. And the next factor, or next greatest factor of 12 would be 24. And 24 doesn't divide 36. So 12 has to be the greatest common divisor between these numbers. I'd get a quotient of 2, 3, and 4. Let's do a little bit of practice of GCD. What would be the GCD? I wrote that wrong. GCD of 56 and let's say 112. So you might want to do prime factorization and stuff, or you could just see that 112 is a multiple of 56. In this case, the greatest common factor of these numbers is 56. Now what if I change this instead to 70? It might take a little bit more thinking. In this case, it's going to be 14. I think one of my favorite tricks for GCD, and I'm not sure like if it always works, I think it should always work, is a quick way to find it. Take the difference of the numbers. In this case, 14. And then the GCD should be some factor of 14. So check 14 itself. If it doesn't work, break it down. So let's say I had 56 and 77 as an example. The difference here is 21. So I check if 21 is the greatest common divisor. It's not, so I break it down. The next greatest factor of 21 is 7. And 7 does divide the 2, so 7 is the GCD. It could be a bit trickier with 3 numbers. I think you'd have to check 2 at a time. Or you can just see it's 12, as in this question. So that one takes a bit of practice. Number 18, I like this one. These ones always appear. So this looks like an absolutely nasty question. Let's change the way we're viewing this question. Change our framing. This 36 is the same as 6 times 6. And aha, this is kind of like question 7. I can pull out a factor of 6 from both of these products. So this becomes 6 times the sum of 1,994 and 6. Well, that should be a plus. And that's convenient because this turns out to be 2,000. 6 times 2,000, 12,000. Usually, when you see a question like this, where it's like, say, some question where it's like almost like a really nice number, like 4,000, where it's almost like that, multiplied by some number, and then you add some other number. Usually you just like round this up to 4,000, multiply by this number, and that's your answer. Like 9 times out of 10, it's going to come out to what you would get if you just round it up. Alright, that's the whole first column of the number sense test. If you were to do the whole first column and have perfect accuracy, that would get you a score of 90. It's 5 points for each question you get correct. So that can be a really good score if it's your first time doing a high school number sense. Now we go to the second column. Okay. So smallest prime number greater than 89. So I think it helps to kind of know like your prime numbers like around like 1 and around 100. So let's list out some prime numbers. So we have pen's not working. technical difficulties. Okay, there we go. So the first few prime numbers are 2, and 2 is the only even prime number. Why is that? Well, because every other even number, 4, 6, 8, 10, has a factor of 2. So because it has a factor of 2, a factor that is not 1 or itself, it can't be prime. 2 is the only even prime. So it's special in that way. And we have 3, 5, 7, 11, 13, 17, 19, 23, 29, and I can keep going, 31, 37, 41, 43, 47, 53, and around 100 we have 97, and we have 89, and we have 83, I think 79, and a few more. After 97 is 101 and then 103. So it helps to know at least like a good handful of prime numbers like that. We want to know the smallest prime number greater than 89. So it's got to be 97. If you don't have your prime numbers memorized, well, you can just kind of think about each number. So no even number greater than 89. So it can't be any of those. It's like, let me show you what I mean. Let's say I'm just checking a few numbers ahead, like 10. 10 numbers ahead of 89. Well, all the even ones are out of the way already, because no evens besides 2 can be prime. Then, anything that's a multiple of 3 can't be prime either. 93, 99, I already crossed out 96. Anything that ends in a 5 can't be prime, because it has a factor of 5. Of course, not 5 itself. Anything after 5 that ends in a 5, it's not prime. And then it comes down to these two. 91 is divisible by 7. 7 times 13. So it's not prime. And you can check 97. It's not divisible by anything. 97 is our prime. Again, this is worst case scenario you have to check. Usually you want to have these, partially memorized. But yeah, that's number 19. 120. Not 120. Question 20. We have this big number. It's an estimation, so let's round and make it easier on ourselves. So I'll say this number for now. Divide by 160. Okay, so a trick I like to do for these kind of questions is if it's like dividing and it's an estimation, I'm going to do long division twice and cut it there and then just add zeros, not be specific with the rest of the digits. So let me show you what I mean. So I'm checking how many times 160 goes into 810. It goes in 5 times. So I subtract 5 times the 160, left of 10. And I drop this 0 down. How many times does 160 go into 100? 0 times. So I'm going to cut it off there. Add the rest of the zeros that I would need. I would just say 5,000. And the range is 4841 to 5350. So we're kind of right there in the middle-ish. A little on the low end, but we're still in range. So we're good. So 5,000 would be our answer for number 20. Number 21. 25 base 10 as written in base 7. So I gotta teach you guys about bases. So what is a base? Well, we use bases all the time. Like the world we live in, like the system we use is base 10. And what it means is that, you know, numbers have place values. And these place values are multiples of 10. So if I wrote a number like 2197, right? I would say that this number here is equal to 2 times 10 cubed, which is 1,000, you know, hence the thousandths place, plus a 1 times 10 squared, plus 9 times 10 to the first, plus 7 times 10 to the 0, which is 1, so the ones place. And so basically, when we talk about base 10, what we mean is these different place values, the ones, tens, hundreds, thousands, are powers of 10. And so what would it mean for something to be in base 7? Let's see. So for something to be base 7, that means it has place values 0 to the 7th, 0 to the 1st, 0 to the 2nd, 0 to the 3rd. It also means that we can't use digits like 7, 8, or 9 because we can only use digits from 1 to 6 in base 7. It's kind of like one less than the base you're using are the digits you can use. So like in base 10, this would be 0 to 6. So in base 10 we can only use 0 to 9. In base 9 we can only use 0 to 8. In base 8 we can only use 0 to 7. Base 7, 0 to 6. We can't write an 8 here because it would be greater. Like we can express it, like we'd have to express the value of 8 using this place value. We'd write it as 1, 1 base 7, or 11 base 7. Because if I did 1 times 7 to the first plus 1 times 7 to the 0, I get 8. And so how would I go transforming a number from base 10 to base 7? Well, the trick is to divide. Let me show you what I mean. So I do 25 divided by 7. That gives me 3 with a remainder, which I'm symbolizing by this R right here. 3 with a remainder of 4. So I'd write the remainder down. Like it's asking what's that number in base 7? I'm going to write down my remainder. So 4. And then I'm going to take my quotient, 3, and I'm going to take that number and divide it by 7. Well, 7 doesn't go into 3, so I end the process and just write the number next to the 4. So 34 is our answer. And I want to make sure you guys understand how to convert here. So we're going to do 2 practice problems. Let's say I wanted to convert about 32 base 10 to base 6. base 6. So how would I do that? Well, actually let's do a bigger number. Let's try 44. Okay, so how would I go about doing this? Well, I'd do 44 divided by 6. What does that give me? Well, that gives me, it goes in 7 times with a remainder of 2. So I'd write down the 2. And then I repeat the process with my quotient. 7 divided by 6. What does that give me? That gives me 1 with a remainder of 1. So I write down the remainder. And then I continue the process with my quotient. So 1 divided by 6. It doesn't go in. So I end the process and I write down this number. So 44 base 10 is 112 base 6. Let's do one more example. So let's say I'm converting (101) base 10 to base, let's do like a big one. You'll see what I mean. Let's get a long answer. How about 14 base 10 to base 2? Base 2 is kind of unique because, well, like we said before, the only digits you can use for base 2 are 0 and 1. So all numbers in base 2 look like 1, 0, 0, 1, 0, 1, 0, 0, 1. That's binary. Binary is just base 2. So whatever answer we get is just going to be a bunch of zeros and ones. So how do we convert 14 to base 2? Well, I divide, and I get 7 with a remainder of 0. So I write down the 0 and continue dividing. 7 divided by 2, that's 3 with a remainder of 1. So I write down the 1 and I keep dividing. So 3 divided by 2, that's going to be 1, remainder of 1, so I write down that remainder of 1, and I keep dividing. So 1 divided by 2, 2 doesn't go into 1. So the process stops, and I write down what I've got, which is 1. So 14 base 10 is 1110 in base 2. And we can fact check that. We can fact check that by using the definition of a base, right? So you have 4 place values. So let's check it, see if it checks out. 1 times 2 cubed, that's 8, plus 1 times 2 squared, that's 4, so I add it, it's 12. Plus 1 times 2 to the first. So that's 12 plus 2, 14, plus 0 times 2 to the 0, it's just 0. So it does check out that this number in base 2 is 14 in base 10. So knowing that can be really helpful for computer science UIL. I think they ask questions where you have to convert numbers to binary, binary to base 10, which, how do we convert from binary to base 10? The fast way. What we did right now is the slow way. There is a faster way. Let's work with that same example. Let's say I was given 1110 base 2 and I wanted it in base 10. So how would I do that? The quick trick, and they'll ask these questions. I'm going to take this number at the very left end here, this 1, I'm going to multiply by my base, so 1 times 2, and then I'm going to add it, whatever product I get, with this next number in line, so this 1 right here. And I'd get 3. I'm going to take that sum, and then I'm going to multiply that sum by 2, so I get 6, and then add it to the next number. So that sum would be the product would be 6. I add it to 1, that sum would be 7. I'm going to take that sum and then multiply it by 2. That gives me 14. And then I'm going to add it to the last number, which is 0. 14 plus 0 is 0. Therefore, my answer is 14. That's how I convert from a base to base 10. You're just repeatedly multiplying, adding, multiplying, adding, multiplying, adding. So, an example here, let's say 37 base 8 to base 10. I just do 3 times 8, it's going to be 24, plus 7, it's 31. It's an easy trick. And it beats just doing 3 times 8 plus 7, which is what we did actually. It's more useful when we have larger numbers. So let's say I had 371 base 8 to base 10. Well, instead of doing 3 times 64 plus 7 times 8 plus 1 times 1, which is kind of long, I can do 3 times 8, it's 24, plus 7, it's 31, times 8, that's 248, plus 1, 249. It's a quick trick. And I guess like to kind of close up on bases, what if I wanted to convert from like base 8 to base 6? So no base 10 anywhere here. I'd first convert to base 10 and then convert to base 6. So let's say I have 71 base 8, I want it in base 6. So I gotta convert it to base 10. 7 times 8 plus 1, that's 57 base 10. Now to get it to base 6, I repeatedly divide. So 6 goes into 57 9 times with a remainder of 3. So I write the 3, and I keep dividing. 9 divided by 6, that's 1 with a remainder of 3. So I write the 3, and 6 doesn't go into 1, so I write down the 1, and that's my answer. I don't know if you guys can hear the TV right now. I apologize if you can. 22. So for 22, I can do, well, let me check if my webcam actually blocked the question. Oh, it blocked 19. And that's what it said. Smallest prime number greater than. My bad, guys. Okay. Moving on. Number 22. I have this number times 19 minus this number times 11. So one thing I can do, I could turn this 11 into a 44. If I did that, I could pull out that factor of 44. And it would just be 44 times the difference of two numbers. How can I turn this 11 to a 44? Well, I can take a factor of 4 away from the 36 and give it to the 11. So it's like I'm dividing this 36 by 4, I turn it into 9, and I multiply 11 by 4 to get to 44. And this expression is the exact same. It gives you the exact same answer. And now I can pull out that factor of 44, be left with 44 times 19 minus 9, which is convenient because it's 10. So 44 times 10, 440. So we had to get a little creative with 22. 23. We have these three numbers repeating on and on forever, symbolized by these dots, right? So we have 0.189, 189, dots, repeating forever. And so when you see three numbers constantly repeating like that, it means that the fraction form of this number, it's those three numbers that repeat, so 189, 189, so 189. It's that number over 990. That's the answer. But we gotta simplify this fraction first. Both the top and denominator have a factor of 9, so we gotta divide by 9. On the top and bottom. 21 over 111. We're still not done. Both of these have a factor of 3, so I divide again. Top and bottom. 7 over 37. That is our answer. So if I had 218 repeating, it'd be 218 over 990. That would be our answer. Similarly, if I have two digits constantly repeating, so let's say I had 0.37, 37. It would be those two digits that repeat over 99 this time. If I had one digit that repeated, like 555, so on, it'd be that number over just 9. So there's kind of a pattern when it comes to this. So, yep. Okay, 24. So we have this expression, divided by 9, and I want to find the remainder. So it could be a pain to work this out sometimes. I think in this case it's an alright question to work out on your own. But the trick I want to teach you has to do with something called modular arithmetic. So if I want to find the remainder of this expression when divided by 5, what I can do is I can get the remainder of each number in this expression and divide it, when it's divided by 5, and then just do the operations like normal, like nothing happened. The remainder here would be 2, the remainder here would be 4, and the remainder here would be 1. And so I could just do the same operations, right? 2 times 4 plus 1. And that's 9, which when we divide 9 by 5, that has a remainder. It has like some number which is 1, right? But we care about the remainder. Remainder being 4. Oh, I forgot to write this right here. And so that's kind of how we use modular arithmetic. So here's another example. Let's say I had an expression like 28 times 22 plus 36 divided by 7. So it could be a real pain to work this out, but if I use modular arithmetic, I would know that this expression simplifies to this. This is 0 because 7 evenly divides 28. So this whole part goes away. I'm just left with 1. 1 is my answer. That is my remainder when I'm dividing this expression by 7. So modular arithmetic is a powerful tool to use. Very powerful tool. Okay, 25. Sum of the roots. So, you probably learned this in Algebra 1. There's a few shortcuts to get the sum and product of the roots without having to do quadratic formula or factoring or something nasty. So, in any quadratic, ax squared plus bx plus c, right? To get the sum of the roots, so sum of roots, that's equal to negative b over a. Just the opposite of the b coefficient divided by the a coefficient. The product of the roots is equal to c over a. And so, it's important to know both because they'll ask both. So to get the sum of the roots of the quadratic 2x squared minus 4x minus 3, well, negative 4 is my b, and 2 is my a. So I'm doing negative 4, the opposite of my b, over a, which that's just 4 over 2, which is just 2. So the opposite of negative 4 over 2, so 4 over 2 is 2. That would be the sum of the roots. What if I wanted the sum of the roots? Here, let me quiz you guys. Let's say I want the sum of the roots of 7x squared plus 14x minus 21. What would the sum of the roots be? Negative b over a, right? So negative 14 over 7, that'd be negative 2. What if I wanted the product of the roots? That would be c over a, so negative 21 over 4, over 7, my bad. It's going to be negative 3. So that's how you can use sum of the roots and product of the roots, those shortcuts. So continuing with algebra, kind of related stuff, is 26. We have f of x equals 9x squared plus 6x plus 1. And I want to find f of 4. What's f of 4? So when it's asking what f of 4 is, that means I'm substituting in 4 for this expression. So one way I could evaluate it is 4 squared times 9 plus 4 times 6 plus 1. But that's the slow way. And we don't want to do the slow way in number sense. We're all about speed here. Oh wait, this is a minus. Fix that. But we don't want to just directly substitute it in. We want to look for a shortcut. And the shortcut is in recognizing that this term right here is a perfect square trinomial. Meaning that it's just equal to, or is it perfect square binomial, trinomial? It's the square of a binomial. I guess perfect square binomial. And this expression is just 3x plus 1 squared. Usually, when you see a question where you want to evaluate some value into a binomial like this, like 9 times out of 10, this binomial here is going to be the square of, or this trinomial here is the square of a binomial. And so how can I tell what this binomial is? How do I know it's 3x plus 1? The way I knew is because I looked at 3 things. There's 3 things you want to check. Oh, and this is a minus. My bad. Make mistakes sometimes. Okay, so how did I know this is 3x minus 1? Looked at 3 things. The first thing, I looked at this first coefficient in front of the x squared. I get the square root of that. I get 3. Second, I get the square root of this last term, this constant term. So square root of 1 is 1. So I get 1. And the third thing I look for is what is the sign here in front of the b term. If it's positive, then I know that my binomial is going to be 3x plus 1. If it's negative, such as in this case, it's going to be 3x minus 1. This is how I can construct and figure out what binomial squared gave me this trinomial. And so, because this is 3x minus 1 squared, it's much easier to substitute x into this expression than it is to plug in x into this expression. Both expressions give me the same answer, but one takes less time to compute. So if I plug in 4 into here, I get 12 minus 1, so this comes out to 11, squared, right? And I come out with 121. It's just a perfect square. Compare that to if I plugged in 4 here, I'd have to do 9 times 16 minus 6 times 4 plus 1. It's just a lot more work when you could be doing way less. So let's do a bit of practice here. I'll give you guys 2 example questions. So let's say I had the function f of x equals 16x squared plus 8x plus 1. And I want to find f of 5. And then I have the function g of x equals 25x squared plus 10. Actually, let's do 20x plus 4. Let's actually make this a minus. Okay. And I wanted to find f of, say, 3. So I'm going to give you guys a few seconds, pause the video, try and find these out by yourselves. If you're back, here's the solution. So this, I take the square root of the 16, I get 4. I take the square root of the 1, I get 1. I check if this is positive, it is, so it's 4x plus 1 squared. I plug in 5, I get 21 squared, which is 441. Okay, now let me check g of x. Square root of this is 5. Square root of this is 2. I check the b term, see if it's positive or negative. It's negative, therefore, this is 5x minus 2 squared. I plug in 3, I get 13 squared, which is 169. So that's how you can do questions like this. Look for those three things: the square root of your a term, the square root of your c term, and the sine of your b term. Okay, so for question 27, we have 64 times 66. So you might be thinking, let's use FOIL, which that's a good instinct to have, but it's much easier to do another trick. So this trick is specific for when the tens digits of the two numbers you're multiplying are the same, and these ones digits, they add up to 10. I know it sounds uber specific, but we'll do a few example questions after this. So here's the trick. So when the two numbers you're multiplying satisfy this condition, the answer is always going to be the product of the last two numbers, so the 4 and the 6. That's going to give me a 24. And then whatever this repeating number is, so 6, times the number like one ahead of it. So 6 times the next number, 7. 6 times 7, 42. And I write the 42 there in front of the 24, and that's my answer. So let's do a few example questions. Let's do 2. What if I had 53 times 57? Let's check if our conditions are true. These tens digits are the same, and these ones digits add up to 10. So I can do my trick. 3 times 7, it's 21. And then what is that repeating number? It's 5. So I multiply it by 1 above it. So 5 times 6, that's 30. That's my answer. Let's do one more example question. Let's do 41 times 49. Let me check my conditions. The tens digits are the same. And these ones digits do add up to 10. So we can do my trick. It's not my trick, I didn't discover it. We can do the trick. So 1 times 9, that's 9. We're going to write 09. You have to write 2 digits each time. So because I got 9, I'm going to just write 09. Got it? That repeating number is 4. So I'm going to do 4 times 1 above it. So 4 times 5, that's 20. So 2009 is my answer. So that's how to do these type of questions. So this was 24 here, and then 42 here. Okay, 28. I'm gonna let you guys try this on your own. I think this is a pretty easy question. We're just gonna work backwards. So pause the video. If you didn't, we're gonna square root both sides. If I square root this, I get 50. I square root this, and the square root and the square cancel out. 50 is equal to 2 times 15 plus k. I divide by 2 on both sides. So these cancel out. This gets me 25 equals 15 plus k. I subtract 15 from both sides. These cancel out. I get 10 equals k. So k is my answer. keep in mind that it wanted the k that was greater than 0. What if it wanted the k that was less than 0? Would there be a k less than 0? There would. Because if I got the negative square root, because negative 50 squared, it does give me 2500 as well as 50. So if I went back here, I'd get negative 50 divided by 2. I'd get negative 25, subtract 15, I'd get negative 40. And if you plug in negative 40 into the original expression, which was 2 times 15 plus, in this case, negative 40, so it's like minus 40 squared. I'd get 2 times negative 15, or negative 25 squared. Since negative 50 squared also gives me 2500. So you gotta be careful for what it's asking for. You want the k above 0 or the k less than 0. Because there are two solutions, so be careful. Be careful. That's a pretty quick one. No tricks to it, really. Okay, so 29, we have this set of numbers, and I want to find what p minus q is, like these missing numbers in this pattern. It's always a pattern, so we got to identify the pattern first, so we can figure out what these numbers are. So if we look at the pattern, we get 1, 3, 6, 10, 15, p, 28, 28, 36, and then q. So let's see if you can identify the pattern. So the pattern, in this case, is we're adding by consecutive numbers. So to get from the first to the second term, I add 2. To get from the second to the third term, I add 3. To get from the third to the fourth term, I add 4. Fourth to the fifth term, I add 5, and so on. So to get from the fifth term, 15, to p, our sixth term, I gotta add by 6. So p is 21. I continue this pattern, I add by 7, 28. I add by 8, 36. So I gotta add by 9 to get q. So 36 plus 9, 45 is q. I want a q minus p. 45 minus 21. That gives me 24 as my answer. These pattern ones could be pretty tricky, but because this is an A test, so one of the first UIL tests that gets released in the year, it's pretty alright. But if you can't immediately identify the pattern, you should probably skip it. Those ones could be nasty. Okay, 30, we have another estimation. So 7 days into minutes. Well, I know in 1 day there is 24 hours, right? I'm gonna just write it hours as HRS. And I know in 1 hour there's 60 minutes. And I know in 1 minute there is 60 seconds. So to get from days, like 1 day, how many seconds are in a day? I have to do a day times 24 hours per day times 60, like I'll show you right now. So we have 7 days. So I gotta multiply by this rate, or this proportion, I guess, that there are 24 hours in one day. And these units of day kind of just cancel out. So, like that. And then I multiply this expression by 60 minutes per 1 hour. Then hours cancel out. And then I multiply by 60 seconds per minute. And so these cancel out, leaving me with just seconds from my original 7 days. I gotta do 7 times 24 times 60 times 60. That's going to be a big number. That might be hard to calculate. So let's kind of think about this. 7 times 24, that's going to be 168. And then the 60 times 60, well, that's just 3600. What I can do is I can round, because again, this is an estimation question. So I can round. I can get away with rounding. So I'm going to round this number. You don't want to round too much. I'm going to round it to 170. And I'm going to keep this 3600. So what I'm going to do, I'm going to pull out those 3 zeros for now. I'm going to do 17 times 36. And then later, I'll add back those 3 zeros. So I'll multiply it by that factor of 1,000 and pull it out. And so I can just FOIL here. So this gives me, yeah, let's practice FOIL, guys. 7 times 6, that's 42. So I write down the 2, carry 4. Then I add the products, the inner and outer products, right? So 7 times 3 is 21. 1 times 6, that's 6. So 21 plus 6 is 27. Plus the 4 I carried, it's 31. So I write down the 1, carrying 3 now. Lastly, I do the last term, so 1 times 3, that's 3, plus the 3 I carried, that's 6. So 612. Now I can add back those zeros. This gives me how many seconds are in 7 days. And I just saw it wanted minutes, not seconds. So, my bad, guys. Okay, we didn't need this last term. Anybody solved the harder question, right? So really we did gain something, didn't we? It was a learning experience. Anyways, getting back to this, redoing it is actually a lot easier. We don't have to really FOIL now. So I still have that 168 term times 60. I'm going to still round the 168 to 170. I'm going to pull out 2 of those zeros and then put them back later. I'm going to just multiply this. This is going to be just 102. Add back the 2 zeros. Boom. There we go. My bad. But moving on, we've got 3 more questions. So I'll probably upload just the first page video, and then I'll upload the second page video probably tomorrow. So let's do these last 5 questions for now. So let x plus y equal 23. Okay. X plus y equals 23. And xy, so x times y, is equal to 76. And I want to find x given that x is greater than or equal to x. So x is probably the smaller number. So I gotta think 2 numbers that add to 23. multiply 76. So let me think. So 23 and 0, no. 22 and 1, no. 22 and 2, no. 21 and 2, no. 20 and 3, no. 19 and 4, yes. So y has to be 19, and x has to be 4. Right? So x is 4. Okay, 32. I want to find b minus c. Okay, so we're just going to expand this binomial. So we're going to do FOIL, but not in the number way, but in the algebra way. So let's square the 4x. That's going to get us 16x squared. And then, let me show you how you want to kind of think about this. I'm going to show you two ways. So there's the FOIL way, and then there's the memorization way. The FOIL way works like this. I have this number times itself, or this binomial times itself. I'm going to do the first terms, so first, outer, inner, last, FOIL. So the first terms, that's going to be 16x squared. The sum of the inner and outer terms, so that's going to be 3 times 4x plus 4x times 3. So that's going to be 12x plus 12x. So that's going to be 24x. And then the last terms, so 3 times 3 is plus 9. I want to find b minus c, so 14, or 24, minus 9. That's going to be 15. That's the FOILing way. But the better way, the number sense way to do it, is memorizing. Binomial expansion. So, it's a good thing to know that whenever you have some ax plus b squared, the result is always ax squared plus 2 plus 2abx plus b squared. Really, let's pay attention to those coefficients. Let's say, like, let me remove the x to make it a little more clean. So a plus b squared is always a squared plus 2ab plus b squared. It's like this little sandwich, the squares and then the 2ab in the middle. So if you remember this, you can get every term off the bat. So looking back at the 4x plus 3 squared, 4 squared, 16, that's the coefficient in front of the x squared term. 2 times 4 times 3 is 24. It's the coefficient in front of the b term. And then 3 squared, it's 9, that's the c term. 24 minus 9, 15. Let's do like one example. Let's add 5x minus 4 squared. Get me the coefficients fast. The way you do it, 5 squared, 25. 2 times 5 times negative 4, that's going to be negative 40. Negative 4 squared, 16. And so, it looks like that. Alright. 33. The LCM of these three numbers. So LCM is kind of related to GCD. GCD and LCM. GCD is the greatest common multiple, greatest common divisor. So if I had two numbers, I want to find the greatest number that divides both of them evenly. for least common multiple, I want to find the smallest number such that it's a multiple of whatever set of numbers I have. So let me do an example. Let's say I want to find the GCD of 6 and 10. Well, let me think what numbers. Let's do the trick I showed you guys. The difference between these two numbers is 4. I check. Does 4 divide these numbers? It doesn't. So it has to be some other factor of 4. The next greatest factor of 4 is 2. Does 2 divide both these numbers evenly? It does. So 2 is the GCD. Whoa. I can't control Z for some reason. So this is 2. Let's say I want the LCM of these same two numbers. What would that mean? I want to find the smallest number that is both a multiple of 6 and 10. So that would be, I could check, I could list out multiples of these and wait till I see an overlap. This would be 18 actually. 4, 30. And boom, right there, 30 is the least common multiple. And I would say, like, in terms of guessing and checking, it's way more annoying to find the LCM than the GCD. But luckily we have a way where you don't have to guess and check. Actually, the way you find the LCM of two numbers is related to the GCD. So you gotta memorize this. The LCM of two numbers, so like A and B, is equal to A times B divided by their GCD. And it's true in this case as well. We could test it out. 6 times 10 over, and we found out their GCD was 2. 6 times 10 over 2, that's 30, which is what we got for our LCM. And so, to tackle this question, we're going to keep this formula in mind. So, we want to find the LCM of 3 numbers, though. We have to work 2 at a time, though. So first, let's find the LCM of 24 and 36. And then we'll get the LCM of whatever that is, and 48. What's the LCM of 24 and 36? Their greatest common divisor, just looking at it, is 12. Right? They got the difference between the two, so their difference was 12. I checked if it was a divisor, and it was, so it's got to be the GCD. So then I could do 24 times 36 over 12. And I'm just going to divide by 12 on one of these, because it's easier to just do, in this case, 2 times 36, then 24 times 36, and then divide by 2. You'd have to do FOIL. That's long for no reason. So I'll just divide one of them by 12. I chose the 24. So 2 times 36. 72 is my LCM. And you can check, it's true. So now, I gotta find the LCM of 72 and 48. So again, I'm gonna use my difference trick. I get the difference between these two numbers. It's 24. Is 24 a multiple of these numbers? I check. It is. That's my GCD. So the LCM of these two numbers is their product over 24. I'm going to just divide one of them by 24 off the bat. I'm going to choose the 48. So 72 times 2, 144. That's my LCM. I recommend practicing writing some numbers, seeing their LCM. Make sure you got the trick in mind. Okay, now 34. How many positive integers between 4 and 28 are relatively prime to 28? What does it mean to be relatively prime to a number? So let me give an example. Let's use 10. Let's say what numbers between 1 and 10 are relatively prime to 10. So I'm going to list out the numbers 1 to 10. So for a number to be relatively prime, it has to satisfy the condition that it has no factors in relation with 10. Now 10, you did the prime factorization. If you did that, you get, it's just 2 times 5. So any number that has a factor of 2 or 5 is not relatively prime. Any number that doesn't is relatively prime. And it's different from being prime, and I'll show you what I mean by that. So off the bat, 2 and 5 are out here. 4 is out because it has a factor of 2, so is 6, 8, and 10. And we're done. Yeah. Remember, 1 is always relatively prime to a number. That's another fact to remember. 1 is always relatively prime. Even though it technically is a factor, it is relatively prime. We just count it like that. And you see that we don't end up with just prime numbers or anything, because we have a 9. 9 is relatively prime to 10. And it's not prime. And the reason it's relatively prime is because it's 3 squared. Those are its factors, and none of them are shared with the factors of 10. So 9 is relatively prime to 10. But we don't want to count. It's tough to manually count, especially for bigger numbers. So we use a trick to count how many numbers are relatively prime. And this trick only works when counting the numbers between 1 and the number itself. And then we'll account for that at the end. But right now, let's answer the question, how many positive integers between 1 and 28 are relatively prime to 28? The way I do that is I'll get the prime factorization, 28, which is going to be 2 squared times 7 to the first. Then I see what prime factors I have. I have a 2 and I have a 7. And here's the trick. To get how many integers between 1 and 28 are relatively prime to 28, I'm going to multiply 28 by the reciprocal of 2. You'll see what not the reciprocal of 2 necessarily, but it's going to be like this number. I guess I could write it like this. This is a better way to write it. So the way we get how many numbers are relatively prime here, we're going to do 2 minus 1 over 2 times 7 minus 1 over 7. Okay. And that's just going to end up being 28 times a half times 6/7. Right? The numerator is 1 less than the denominator. The denominator being the prime factors of the number. Keep in mind, it doesn't matter what this exponent is. It could be 2, it could be 21 million. I'd still do this to get the number of relatively prime factors. And so I evaluate this, and I'll get, well, half of 28 is 14. Divide by 7 times 6, that's going to be 12. There are 12 numbers between 1 and 28 that are relatively prime to 28. So again, how did I get these fractions? The denominator is the prime number, like the prime factors of 28. And the numerators for each of these fractions are one less than the denominator. So I add the prime factors 2 and 7. So it's 2 as the denominator with 1 as the numerator, and then 7 as the denominator and 6 as the numerator. Okay, but that tells us how many relatively prime numbers between 1 and 28 are relatively prime to 28. I want to know, the question wants to know, how many positive integers between 4 and 28? Between 4 and 28 are relatively prime to 28. And the way I find that is I gotta account for those numbers 1, 2, and 3. And I gotta subtract them from these 12 numbers. Subtract them like I gotta see which numbers are relatively prime and subtract it from 12 because it doesn't fall in that range. So let's think. 1 is always relatively prime, so I gotta get rid of that because it's not in range. 2 is not relatively prime because it's a factor of 28. 3 is relatively prime though, so I gotta subtract that because it also doesn't fall in that range of 4 to 28. And then that's it. The answer I get is 10. There are 10 numbers between 4 and 28. 12 numbers between 1 and 28, but only 10 numbers between 4 and 28 are relatively prime. So now you know how to find, you know what it means for a number to be relatively prime now, and how to find how many numbers between any two numbers are relatively prime to that number. And the last trick, it's also memorization. This one's just memorization. You gotta know your cubes. 1 to, I would say 16 is good. So, memorize. Squares 1 to 30, cubes 1 to 16. Got it? And 3 cubed, or no, 7 cubed, that's 373. 5 cubed is 125. So this difference is just 218. You gotta have these memorized, guys. Alright, so that concludes the video for today. Hope you guys learned a lot. If you have any questions about anything I've covered here, ask me in the comments below, and I'll see you guys later.